All right, we'll go ahead and get started by taking a look at our calendar. Today is March 13th. Ignore the calendar on the bottom right of the screen. Today we talk about areas and volumes. Hopefully we're working on project 4. I'll go ahead and give a hint right now at the very start about project number 4. So we begin on page 21 in the packet. And you've been thinking a lot, hopefully, in this project about this thing called the gamma function. So I've put the definition there. And question number 5 says, explain why gamma of 1/2 converges. I made a typo on page 21. So if you can cross that off, it says gamma of 1 in the packet. It should say gamma of 1/2. That's what the question in the project is. So we want to prove that gamma of 1/2 converges. And there's this hint about breaking the integral up into an integral from 0 to 1 and another integral from 1 to infinity, and then using a comparison test for each of those two integrals. So let's go ahead and do that. All right, so let's go ahead and write down the formula for gamma of 1/2. So we'll begin by just using the definition right there at the top of the page. So all the x's become halves. So this just is the integral from 0 to infinity, e to the minus t, and then that x right there becomes 1/2. So when you plug a 1/2 in for that x and subtract 1, it becomes t to the minus 1/2 dt. And I'm going to rewrite this integral. I know we're supposed to split it up, but before we do, I don't like having negative powers. I don't quite understand them, so I'm just going to make them positive and put both of these guys downstairs. And now we're going to split this up. And the reason we're going to split this up is that there are two different problems with this integral. On the one hand, anytime you have an infinity, you got to do some work. We have an issue with this infinity, and we'll deal with it by replacing it with a letter b. But the other problem here is the 0. And the 0 is a problem because that gives you an undefined fraction. So we're splitting it up so that we can really isolate those two separate problems. So the hint says go between 0 and 1. Copy the whole radicand, not radicand, integrand, plus, and then the other integral must then go from 1 to infinity. And now we're supposed to do a comparison test on each of these two different pieces. So let's look at the second integral first. In the second integral, on the bottom, I see a t to the 1/2, and I also see an e to the t. And if you go back and you look a few pages earlier, you'll find that list of the things the book calls the useful integrals for comparison. So we can just jump back a few pages to find that list. It's right here on page 17. So again, the integral that we had was 1 over e to the t to the 1/2, and this was going between 1 and infinity. So if it were just an e to the t down here, and you see something that looks like an e to the t down there, in our case it's just a 1t, so would that integral converge or diverge? It's going to converge because anything positive downstairs, it converges. So the question is, well, what about the other part? What if it was t to the 1/2? And that was the only thing down there. So t to the 1/2 you will find here. You got to mentally translate the x is really a t in our case. The power is a 1/2. Does that converge or diverge? That one diverges. So the question is, who wins? Well, it's easy to just look at it and say, well, e wins. E always wins. But that's really not the important thing here. The important thing here is to compare. I definitely want to choose to compare to this thing because apparently, according to the question, this integral converges. So we want to compare to that, and then the question is, how does this original fraction compare to this fraction, the one that we're interested in? Well, we've stuck some more stuff into the denominator. We've made the denominator a little bit bigger. So what happens to the fraction? It's a little bit smaller. So the thing we're interested in is smaller than a convergent thing. Super. That's exactly what I wanted it to be. So it's not really a matter of picking the dominant thing. It's pick the one that you want. You wanted to pick the one that converged. So let's pick that. And actually the t to the 1/2 makes it a little bit better. So that's the first integral. The second integral, well, that was actually the second one. The first one was the same thing, but between 0 and 1. 1 over e to the t to the 1/2 dt. Okay, for this one, we are again looking at two different things. So I'll circle the 1 over e to the t, and I'll ask, is that this rule? And the answer is no. And it's not that rule because of the limits. The limits for this rule involve any number up to infinity. There's no infinities in this integral, 0 to 1. In fact, the e to the t, nothing special is happening between 0 and 1. So e to the t is pretty irrelevant. The reason this integral is tough is because there's a t in the denominator, in that t to the 1/2. And 0 in there makes it undefined. So the e isn't going to help me or hurt me. It's just sitting there doing its thing. It's not very interesting. It's really the 0 part. So does the 0 part bother me? Let's go ahead and look at this integral. And because it's a 0, I'm in this middle rule in my list. So the power is 1/2. Does that converge or diverge? That one converges according to that middle rule because p is less than 1. It's 1/2. And then the same thing that we said before is still true. So now I'm trying to compare the thing that I now know converges to the thing that I'm interested in. In this denominator right here, we've stuck an e. We've made it a little bit bigger. So what have we done to the fraction? We've made it a little bit smaller. So again, it works out just perfectly. It is smaller than something that I know converges. So we'll leave it to you to write up all the details. We've written things very informally here, but we've got the heart of the matter. Leave it to you to write things. You'll have to take limit as b goes to infinity or as b goes to 0. Write it all up, but hopefully we're convinced that we have two integrals that converge. So the other part of the project that I wanted to give a quick hint for was number 8, the very last question. And so I didn't include this in the packet, but I decided I wanted to add it to this video. So question number 8 from the project says, prove that gamma of 0 diverges. Just prove that gamma of 1/2 converges. But it turns out gamma of 0 diverges. So we're going to give a hint to this one. The hint in the project says do the same thing as before. Split it up into two different integrals. So that part's easy enough to do. We'll go ahead and first write what gamma of 0 is. Plugging the x, instead of the x, we'll put a 0. So this becomes integral 0 to infinity, e to the minus t, t to the -1 because x is 0. And again, I don't know what I'm looking at with these negative powers, so I'm going to put them both in the basement. Like that. Okay, so apparently this thing is supposed to diverge. And the way we're going to get there is to split it up again because we've got two separate issues. There's the 0, which is a problem here because I can't divide by 0. And then there's the infinity, which is just a problem in general. So we're going to split it up into two different things. Again, splitting it up at 1. That's what the hint says. So we'll go 0 to 1 of all that. And then 1 to infinity. Okay, so looking at this, again, we're trying to prove that this integral diverges. Let's just think a little bit about the logic here. Suppose that this one over here converges, which means it's a finite number, and this one over here converges, which means it's a finite number. Then what would you say about the sum of those two things? It converges. It's going to be some finite number. If they both happen to diverge, it would be an infinity on the one plus another infinity on the other. What would the sum be? Very divergent, infinity. But what if the first one converged to some finite number and the second one diverged? What would the sum be? It would be divergent. So we don't need them both to be infinity. We just need one of them to be infinity. And it turns out that's very good because the second one actually turns out to converge. So you can go through the details of the comparison test, but that second integral right there converges. So that's not the part that's going to help us. What that means is that what we have to show is that the first integral diverges. First integral is infinity. Okay, so looking at this first integral, I'm thinking about it, and I see a 1 over t. So if I just think about comparing to the integral of 1 over t, dt between 0 and 1, that's in our list of useful integrals. Does that integral converge or diverge? It diverges. It's right on the border. It's the last one that diverges, or the first one that diverges, but it diverges. So I feel like the one that we have is probably also going to diverge because it's very much like this 1 over t. But the problem here, the reason this is tricky, is that 1 over e to the t times t, that's what I'm interested in, and 1 over t, which I know diverges. Let's see how they compare to each other. We've put e to the t in the denominator, so we've made the denominator is bigger, so the whole fraction is smaller. So the integral that I want is a little bit smaller than infinity. That is useless to me. The direction's going the wrong way. So here's a trick. We haven't discussed it in class, but it turns out to be important in this example right at this moment, is that we actually have some information about this e to the t business. E to the t is only happening between 0 and 1. We're going to make use of that right now. If t is between 0 and 1, which is the only t's that we care about in this problem, then e to the t is trapped between what two numbers? E to the 0 and e to the 1. Yes? Okay. So we continue. I'm still trying to build a 1 over e to the t, because that's what we had before. What is that trapped between? Yeah, so we'll flip over that, and then we'll flip over this guy as well, right? Actually, so yeah, we're going to flip over this. This is a 1 over e to the 0. Flip over this, 1 over e to the 1. What happens to the inequalities when you put 1 over? They change. So now it goes this way. And then finally, remember the whole goal was to build this fraction. So the only thing I need to do is stick some t's on the bottoms. So I'm quite happy to multiply this whole thing by 1 over t to put some t's in the bottoms. So then our last conclusion here is that 1 over e to the 0 times t is definitely bigger than 1 over e to the t times t. That's the thing I've been trying to build, which is definitely bigger than 1 over e to the first times t. And again, we were hoping to get some divergent thing because we believed that that this integral, right, whoops, that's not a highlighter. We believe that that this integral right here diverged. So what I'd really like is for the thing that I have to be bigger than the divergent integral. So on the one hand, this thing right here that I have is smaller than that guy. That's not helpful to me. But look, it is bigger than this one. And so I'm not going to take this all the way to the end, but we are going to use this fact right here. You have the integral that you want is bigger than 1 over e to the first times t. So we're just going to say, think about, yeah, that's right. Think about this integral right here. And if you can prove that that integral diverges, then the one that we have, which is a little bigger, must diverge. So there's a little left to do on that one. So think about that one. If it helps, this question stumped me when I first saw it. I grabbed it from my predecessor, Curtis, and I tried and I tried and I tried. I kept getting the inequality to go the not helpful direction. So at some point I called him up, Curtis, how the heck did we do this problem? He said, oh, do that. Okay, good. All right. So let us move to the next page with those hints behind us. And we'll start with number 2. This chapter is all about applications of the integral in geometry, physics, economics, and probability. I'm just going to stop reading that. So pause the video, read this, and then come back to the video. So we're going to jump down to number 3 once you've read all of this stuff about formulas and applications of the integral. And we're just going to think about Riemann sums and this idea of slicing. We're going to use that word a lot in the coming classes. And again, I'm just going to give kind of a highlight view here. Ultimately, what I'd like to do is get us to the point where we remember, or we can understand what all of those symbols have to do with finding the area under the curve. We've seen them before. It's a lot of stuff in the beginning, but if you break it down into pieces, it's not so bad. So I'm just going to draw one right rectangle here. That one happens to overestimate the area under the curve there, but that's okay. And we gave a name to the width of this rectangle. We called that width delta t. Turned out it was b minus a, those are the endpoints, but excuse me, divided by n. N was the number of rectangles. So we'd seen that formula before. And the width of that rectangle is delta t, and the height of this rectangle in this case is f of t1, because that's how I drew my rectangle. But in general, the height could be f of t anything. So this is our way of writing f of some general t times delta t. This is a height, and this is a width. And we multiply those two together, we get the area of a single rectangle. What does this symbol right here mean? It means sum. You're going to add up all of those areas that you calculate. And then finally, what's going on here? Yeah, infinite number of little widths, infinite number of rectangles. And if you do infinitely many of these razor thin rectangles, that's what we call the area. So it's literally a definition for the area under the curve. It's that thing. Super. And so then instead of writing all that stuff, we decided we were going to write this symbol right here. We've seen it for many weeks now, and we've maybe lost the association with area. We're just so used to doing antiderivative when we see that symbol. But initially for us, that symbol actually meant area under the curve, and we used it instead of all of the blue highlighted stuff. So those two blue highlighted things are exactly the same. We just defined the integral symbol to mean all the other stuff that's in blue with the summation. And then one little translating thing that's going to happen here is we're just going to make some associations between the crazy limit stuff and the actual integral symbol shorthand. So how do the pieces go together? Well, this delta t, it looks an awful lot like which part? Like the dt. Super. This f of ti looks like f of t. This summation symbol, different color, is the Greek letter for sigma, which is the Greek letter for s. And our letter for s doesn't look so far removed from the integral sign. So that's another translation. Okay, the pieces that don't really translate very well, the limit doesn't appear, it's just embedded inside of the integral symbol. And also the a and the b, I'll put question marks, they come from the problem, but you don't actually see them so much in the limit way of writing it. Okay, so there's a process here in number 5 that talks about slicing. Again, you can read it later on. We're just going to jump into some examples, but know that there's a process that you can come back to here. After we do a couple of examples, maybe read through this process, and hopefully it'll make some sense. So number 6, let's find the areas of these figures by first writing a Riemann sum, and then rewriting it as a definite integral. For the middle example, we'll do the integral on the calculator. These figures and many other figures in this packet of notes are scanned from your textbook. So let's go ahead and take a look at the first one. We've got a triangle, and the goal for each of these is to find the area. So this is a very silly example to use Riemann sums for and calculus for because it's just a triangle. And so let's just go ahead and write the answer up here. Area of a triangle we know is half of the base times the height. How much is the base of this triangle? It's 6, right? It's normally down at the bottom, but it's written at the top. So we go half of 6 times, what's the height? 3. So the area there is 9. That problem is done far more efficiently than we're about to do it. But we do an example the inefficient way because on one that we could just do easily, just to convince ourselves that this thing we're about to do actually does work. It gives you the right answer. And it'll turn out that what we're about to do will help us get right answers in many places where there's no way to just plug and chug into some simple formula. So the basic idea to find the area of this shape, this triangle, is we're going to cut it up into lots of thin slices. That thing right there is very close to being a rectangle. I'm going to call it a slice for the next month. And what we'll do is think about the area of one slice, one rectangle. And so the area of our slice, our rectangle in this case, is base times height. It's a rectangle. And let's go ahead and write the height. The height is the base in this case is symbolized by delta x. So there's a delta x there. And the height is the part that we got to fill in. And this is the part that requires some work because the height of that slice is very different from the height of that slice. So the height of the slice depends on where the slice is, yes? And so the height of the slice is going to turn out to be a function of some variable. In our case, that x is defined to be like telling you where you are in this triangle. So what we're about to do is come up with a formula for the height in terms of x. So find h in terms of x. Okay, so let's see if we can do it. One way to do it, I'm not going to do it this way, but if you really like Cartesian coordinates, you can superimpose a set of x and y axes on here, and you can actually find the equation of that line. Right? You know that up here it's at 0, 3, over here it's at 6, 0, and you can find the equation of the line. And right there will be the way to relate the height of the slice to where the slice is in the triangle. I'm not going to do that, but you're welcome to do that. What we're going to do is use similar triangles. I'm going to call this thing right here h, the height of my slice. It's not a constant, it's going to change. But let's use similar triangles here. So we know that this small triangle is similar to the big triangle. So we're just going to write a proportion. So for example, we could say that h is 2, and what's the side that's like h in the big triangle? It's 3. As, and then we'll pick a small side of the small triangle, x over the same side in the big triangle is 6. That's the relationship. And so you can cross multiply there. Ultimately, we're trying to solve for h. So we should get h is equal to half of x. Which I think makes a lot of sense because this 3 is exactly half of that 6. This height is exactly half of that x. It's the same, you know, like that's the relationship. Okay, so that means that we can take that thing down there in blue and stick it right here. We were just waiting on base times height, and we just found the height. The height we just figured out is 1/2 of x. So this guy ended up getting plugged in up there. Okay, so that's the area of one slice. It's delta x times half of x. That's the area of one rectangle. We're going to find the area, oops, we're going to find the area of all the slices. And I need way more room for this question, so I'm going to go to another paper for the other two examples. So the area of all the slices, well, what is it? It's just the sum of all of the things that look like that. Delta x times 1/2 x. Okay, so technically we should stick a little I down here to say that we're counting these x's. The first x is x1, x2, x3, x4. I goes from 1 to n. I'm not so worried about the i's. They're going to disappear as soon as we go to an integral, but we'll just stick it in there. And so then finally the area, the actual area, these slices are just approximating the area. The actual area is when you send the number of slices to infinity, and we just replace that thing with an integral. So what happens, this delta x becomes what in the integral? It becomes a dx, and the 1/2 x sub I is just the function. The function just got copied in here, but we lose the I that we artificially brought in anyway. And so we'll just draw some arrows. This guy is there, this guy is here. And the last thing is the limits. What's the smallest x? You got to go way back to the original picture. What's the smallest x value that makes sense here? 0. And then what's the biggest x value to capture the whole thing is 6. So we're going from 0 to 6. Okay, 1/2 is a constant multiple. I'll keep it right there. Integral of x is squared over 2. And we're going between 0 and 6. So we plug 6 in, it becomes 6 squared. I'll mush those 2's together. It's a 4 downstairs. Minus 0 squared over the same 4. And we get 9. Okay, again, the goal of this is not to show that it's better to do it this way than to find the area using the triangle formula. It's way better to find it using the triangle formula. But this way works, even though we actually never had the right area until we actually had infinitely many rectangles, because every one of these slices misses a little bit of area. But if you do infinitely many of them, you get all the area and it works out perfectly. Okay, let's try the same thing, but for the circle. So I'm going to go to the next page and I'll grab a snapshot of that photo. Okay, so here's our picture, trying to find the area of the circle. Again, it's a circle, so there's an easy formula. Formula for the area of a circle, pi r squared. Happy Pi Day tomorrow. Pi times the radius of this circle is 3. So 9 pi is the correct answer. We can type it in the calculator and get a decimal. So we'll type in 9 pi, 27 and then some change. So let's see what we get here. All right, 28.274. Super. Okay, so that's the right answer. And again, we're not going to get there better. We're going to get there way slower, but we're going to get there using this completely different technique. So, and this might be even a little bit more surprising, because what we just did before was approximate a triangle with rectangles. Okay, that's not so great, but at least the triangle is straight lined, whereas there's nothing straight in the circle. And so we're going to approximate something completely round everywhere with completely straight rectangles. And we're going to get to the right answer. So the slice has been drawn. It's this thing right here. It is very similar to being a rectangle. You can ignore the curved ends. We're just going to treat it like a perfect rectangle. The width of this rectangle, so we'll start the same way we did before. Area of one slice equals, it's a rectangle, so it's base times height. And in fact, maybe I'll use length and width for this rectangle. This rectangle is going side to side. I'll call it length and width. Okay, the width of the rectangle is given. It's a symbol. What symbol is it in this picture? It's delta H. So I'm going to copy that delta H. And have we seen this before? That kind of like it's just too small a space to stick the symbol in. So maybe we've seen that represents delta H. And what needs to go in here is the length. Now it turns out it's quite challenging to find the length, but the length is, I'll just draw it here in red, from here to here, and I'll call it L. But does that length stay constant as the rectangle slides up and down? No, it changes. And it's very much dependent on our variable here, which is H. So what we're trying to do is write the length in terms of H. I'd really like to be able to put something with H in those parentheses there. So we have to use the fact that the radius of that circle is given. It's 3. And what we're going to do is maybe instead of drawing this radius here, which is just out in the ether, we're going to draw a radius that goes up and has something to do with our slice. So we draw that radius. How long is it? It's also 3. I will also draw in another color a line that goes straight up to my slice. How long is that? It's not a number. One half L is definitely important here, so we can bring that in as well. I'll say that from here to here is definitely 1/2 L. That's going to be useful to us. Yeah, we're going to use Pythagorean Theorem, but we need to label the purple thing. What letter goes on the purple thing? It's given in the picture. It's H, right? H is the vertical distance, which we've just brought over into our circle. Right, so we use Pythagorean Theorem on that right triangle in there. So it goes H squared plus the other thing squared is equal to 3 squared. And make sure you get that hypotenuse by itself. So that means that the other thing squared is 9 minus h squared, subtracting the h squared from both sides. So the question mark is root 9 minus h squared. That's half of the length. So then inside of here, we were supposed to put the full length. What do I do with root 9 minus h squared? Multiply by 2. So right in here we go 2 root 9 minus h squared. That's it. So translating that whole thing, that expression for the area of a slice into a summation, a sigma, and then into an integral is pretty straightforward. The hard work is getting to that expression. Find the area of the slice in terms of a single variable. That's the hard part. Okay, so we've got the area of one slice. If we decided to add up the area of all the slices, I'm just going to copy that formula that we wrote up there. And just for kicks, I'll go ahead and put a little subscript on the h, the variable. So that's the area of, I should have said all the slices, not just one slice. Area of all the rectangles that aren't drawn. And then we'll translate this to an integral. Again, the delta h becomes dh. 2 root 9 minus h sub I squared. Just drop the I. And then in terms of the limits of the integral, we're going to figure out what's the biggest h. So h is this distance here. So what's the biggest h that gets us up to the top of the circle? Is a 3. So we'll put a 3 up there. How about the smallest h? Yeah, if you're willing to put -3 there, I think we'll get the right answer by letting h equal -3 at the bottom. If you don't, if you don't like putting a 0 there, no, you cannot go 0 to 6. We can't do that. But what you could do is go 0 to 3 and then double it. So if you prefer to use the symmetry of the circle, you go 0 to 3. I actually haven't checked this, but I think we're going to be okay just doing -3 to 3. So turns out that integral is one that I'm not sure how to do. Let's just go ahead and use the calculator. The directions here said use the calculator on the middle integral. So I've got right there what the answer was. That was our 9 pi. We know that's the right answer, so hopefully with the video recording we'll actually get the right thing. So we're doing 2 square root of 9 minus x squared. I need parentheses, comma, x, comma. All right, we're going to cross our fingers that -3 to 3. Okay, let's find what happened here. Cross our fingers that -3, comma 3 will work. Okay, I think we've typed it in right. We were expecting that 28 point something answer. This is the part where I get nervous because I don't actually know. Usually I know what's going to happen before I get to class. This must be a hard integral. The calculator is really churning through. All right. And just because I lost it, 9 pi is what the right answer was. And there it is, pretty close. Calculator is approximating too. So this is about 28.274. Really surprising to me that we can use a bunch of rectangles to estimate the area of a circle, something completely round. Okay, so we'll go back. I'm going to go ahead and skip the third picture. It's the same idea. I'll give one little hint if you decide you're going to do some work on this and try to write this one out. Again, the area of one slice is it's the base times the height. And the base in this picture is delta x. That's easy. But the height of the picture, the height of the slice is this distance right here. Would you say that that distance right there, is it a change in x or a change in y that represents that distance? It's a change in y. It's a vertical. So what you need to do is figure out how much y is at the top and figure out how much y is, so there's y at the top, Got to figure out how much y is at the bottom and do what with those two numbers? We're going to subtract them. Pay no attention to the fact that part of this shape is above the x-axis and part is below. It makes no difference where those things are. The fact is, this vertical distance is always y at the top minus y at the bottom, regardless of where this shape is. So what do you have to do? You got to solve for y in two different places. On the one, it's already done. Y at the bottom is always x squared minus 4. And the other, you got to do some work. Y equals, just solve for y. So I'd encourage you to try that one later on and see if you can get to some reasonable answer. Okay. Oh, one other thing that's important here is that in order to take this rectangle and sweep it left and right to get all of the shaded area, you need to know how much x is at the far left. How much is it? 0. You also need to know x at the far right. It's not given. You got work to do, just like on the project about all those areas, project 2. You got to find a point of intersection. Okay, moving on to number 7. Same Riemann idea, but now we're going to find the volume of the solid pictured. Used to be more than one example here, so this is just a single volume. And again, we can use the calculator once we've set up the integral. So it's a 3D thing. It's not a very complicated 3D thing. It's just a cylinder, and there's an easy volume formula for the cylinder. But again, the idea is that we can use this technique for things that aren't easy, that we don't just have formulas that we know. So the idea is we're going to draw maybe not a slice, but a slab. So this 3D thing that's kind of in the middle of this floating object, I'm going to call our slab. And it is pretty close to being rectangularly shaped. It's a volume, so it's got 3 dimensions now. There's a length and a width and a height. But essentially, we can ignore the curved parts of this. We can just pretend that that's a straight up and down thing. Okay, sure, we're missing the cylinder by a little bit, but the slabs are going to get thinner and thinner and thinner, and the error will get smaller and smaller and smaller. So instead of thinking of area of a slice, it is now volume of a slab. Okay, so the volume of a slab. So for us, the slab is basically a rectangular type thing, length times width times height. Let's see if we can grab the easy parts of this. Let's see if we can use different colors here. So I'm gonna call this guy right here the length, and this back here can be the width. And then in red, we can say that this distance right here is the height, okay? Length, width, and height. 2 of these guys are very easy. How much is the length? Sorry, that's the hard one. How much is the width of all of those? They're all 10, right? Imagine taking that slab and sliding it up and down throughout the whole half cylinder. The width is always 10. So I'm going to leave a big blank here because the length turned out to be hard, but the width is 10. The height has a name. There's symbols up there. What is the height? It's delta, yeah, I would call it, yeah, delta y in this picture. Delta h is fine too. And the hard part is the length, because as you slide that slab down, the length gets longer, gets bigger. And as you slide the slab up, it gets smaller. So it's going to be something in here with what letter? Yeah, length in terms of y. That's the goal. And the length in terms of y. Okay, so I'm going to draw just the 2D looking straight at this shape, so all we see is the circle. We don't see any thickness. And then I'm going to get rid of the bottom half of it, so all we see is the top of the circle. And up here is my generic, I don't know what's going on, but that's where the slab is. And what else can we say? We can say that from here to here is how much? 7, because it's given to us as 7. Well, that radius isn't so useful, but we'll do the same trick where we connect to the slab. That is also 7. This distance here to here is given a name in the first picture. What is that distance called? Yeah, from here to here is this distance, which is called y in the picture. So we've got a y, we've got a 7, and then the length is part of the unknown. So we'll call this guy right here the question mark. We'll play the same Pythagorean theorem game as we did before. I'll leave that to you. But it's going to turn out that the question mark is the square root of 49 minus y squared. So then what do I do to that to find the length of the whole slab? We'll double it. So right in here we go 2 square root of 49 minus y squared. Okay, so then translating that into the volume of all the slabs, that was just the volume of one slab. You want to add the volumes of all the slabs, then you just copy everything that you had before. And then again, I'll put in my silly little index I. It's really silly because in the integral, I'm just going to take it out again. So that expression represents our approximation for the total volume because we've added all the slabs together. Then we translate into an integral. So the volume is actually equal to the integral. We'll copy everything inside of that sum. Drop the silly I. Delta y becomes dy. And then the last thing we have to think about are the limits of integration. And you got to go back to your picture and ask yourself, what's the smallest y? This distance right here is y. What's the smallest y that makes sense for that bottom slab? 0. For the top slab, what's the biggest y? It's 7. So we're going 0 to 7. Okay, so we'll end that one right there. You can just type it right into the calculator. I can't tell you how to do that integral, but calculator can give you an estimate. If you know how to find the volume of a cylinder using some basic formula, you can then check your estimate. It'll have pi in it. Okay, moving on to the next page. I think we're done. Are we done with that page? Yeah. Okay, so moving on to the next page, we're going to get to problems that we couldn't have done before. All the shapes we've seen so far, we just had simple formulas. Area of a triangle, area of a circle, volume of a cylinder, all known. But now we're going to get to these problems that are called volumes of solids with known cross sections. And there's a little warning there. It says cross-section problems are typically hard. So let's just jump down to number 10. We'll come back to 9 after we finish or when we need it. So let's come to number 10. Find the volume of the top 2 feet of a 10-foot diameter sphere. The volume of the top 2 feet of a 10-foot diameter sphere. And even though it's a pretty easy thing to understand, to visualize, so we'll go ahead and draw our sphere. We've got our sphere, the radius is 10 feet, and we're interested in just the top 2 feet. So up here, I'm going to erase this in a moment, but I just want the top 2 feet, right? From here to the top 2 feet. Do you know a formula for the volume of part of a sphere? I mean, I can't really cut the sphere any nicer than that. I just one straight cut. But do we have a formula for something even easy like this? The fact is, there might be formulas out there. I haven't seen one. And the people that came up with those formulas maybe did what we're about to do and then just came up with a formula from that. So even easy things like this, like you just think about the formulas that we know, they are few and far between for areas and volumes. So I'm going to erase that picture because I'm going to have other stuff. I don't want to clutter my diagram. So in this setup, we're going to have to draw our own slices. So it's already harder than the ones that we did where the pictures were given. So let's just go ahead and draw a regular slice, and a slice for us, we'll go ahead and slice this way. I'm not so worried that that's probably below the 2-foot line. I'm just drawing it at some general place. and then we'll force it to be at the top at the end. And again, part of the hard part is to come up with letters. You need to introduce some variables here. So let us say that we're probably going to do the same trick where we connect from here, maybe not to the right, but to our slab, our slice. How long is that all the time? That's always 5 because it's a 10-foot diameter. So the radius is half. And it feels like we're going to need to give a letter name to the distance from that center to this center. So let's pick a letter. How much? Okay, we'll call that one Y. And then if it follows the same pattern as before, we're probably going to be able to figure out what that red length is equal to. So you can just dive into Pythagorean right now. For me, I need the motivation first, so I'm just going to start thinking about the volume of my slab. And actually, I'm not even going to draw the slab. All I've drawn is one circle in purple at the top, but technically I should have drawn it with a little bit of thickness. So it shouldn't have just been that circle, but it should probably be another circle right on top of it. But it'll clutter the picture, so I don't want to do it. But I guess I will say I'm happy to call the thickness delta y, just to give it some symbols. All right, so the volume of one slab, it is a, we got to think about the shape of our slab. The shape of our slab is essentially like a penny. It's two circles stacked right on top of each other with very little thickness in between. All right, what's the math word for the shape that a penny takes? A circle is a 2D thing. You got to make a 3D thing. It's a cylinder, right? A penny is a cylinder. So the volume of our slab, we need to know the volume of a cylinder formula. That's what we're using. Okay, so you can look it up, or you can think of a cylinder as being a circle stacked on top of other circles. So anybody able to know or figure out? Pi r squared h, good. And so this is a good time to say every slab is not just length times width times height. It really depends on the shape of the slab. But hopefully the slab that you've drawn is something with a shape that you know the volume formula for. Okay, so pi r squared h is our volume. So let's start filling some stuff in. The pi is a constant. The r, I'm going to put in red here because the r of our cylinder is that distance that we don't know. So we are going to have to fill that in. How about the height of our cylinder? As we call the delta y. So we'll put that at the end as the delta y. So right in here, we're looking for r in terms of what letter? Yeah, in terms of y. And maybe also starting to see the pattern that the delta letter is the same one that you need to get everywhere else. That's the only letter you're allowed to play with. Okay, so we'll do our same Pythagorean theorem thing as before. You can slow down the video and check to see you get root 25 minus y squared. Okay, so here's a question. In the other cases where we had this picture, we would take the root 25 minus y squared, but in every other one we've done today, we'd double it, right? Because we've got, it's two of those. Do we do that here? No, the formula for the volume of a cylinder has r and doesn't have the diameter, doesn't have a total length in it. So again, you really can't, it's not formula based. You really have to think about the shape and think about what you're trying to find. All right, the rest of the problem is pretty formula based. That's the hard part, setting this thing up. So let's jump past the summation notation and we'll just go straight to the integral. Integral, so we're copying everything from up above. Pi root, okay, let's erase that too because we don't want it. So pi root 25 minus y squared, delta y, sorry, that becomes dy. And then all we need finally are the limits. Again, thinking about how we defined y completely determines what numbers go here and here. We wanted the top 2 feet of this sphere. So all that stuff up there. What's, oh, I apologize. Thank you. Thank you, thank you. So this should have been r squared, and I never squared my thing. So it should have been this guy. I'll erase this and fill it in. It should be this guy squared, and then a delta y is at the end. So that means that this guy gets squared. Thank you. All right, and then the limits of integration. We said we just wanted the top 2 feet up here. What's the smallest y? It's 3. You got to think about it, right? You got to think about it. So the smallest y, yeah, because it was 5 was the radius. So the smallest one is 3. What's the biggest one? Is 5. And so we're going here from 3 to 5. And we could have perfectly well defined y to not be the distance we had, but we could have said y is the distance from the top. And we would get a different looking integral and different numbers for the limits. What would the limits be for this y? 0 to 2, right? So you really have to think about your picture. And you make choices, and there are different correct ways to go about doing this. One kind of cool thing about this, we're not going to finish this one, but the square and the square root, they cancel each other. And so you actually get an integral, one of the rare ones that we can do without the calculator, which is kind of neat. You can find the volume of that top 2 feet without any technology. Okay, let's take a look at number 11. Find the volume of the solid whose base is the region inside of the circle x squared plus y squared equals 4, and whose cross sections perpendicular to the x-axis are squares. I'll do my best to draw this on the board, but we'll look at a Mathematica demonstration to really get a good look at this thing. Okay, so let's see. First, we're going to draw x squared plus y squared equals 4. Now, it's tempting to just draw that the normal way on the normal x and y axes. So x squared plus y squared equals 4 is a circle whose radius is 2, but I'm not going to draw it in the standard way because we're going to have a shape that's coming out of the board, out of the computer screen. And if you just draw it this way, technically you can't see anything if the shape is coming out of the board at you. So what we're going to do is take these axes and lie them flat. So the way we lie them flat is to draw the y-axis at an angle, imagining it's going off into the distance. And so in this case, we have a radius of 2. So I'll go ahead and draw 2 hash marks going this way, same 2 going this way, same 2 up here, and 2 down there. And so our circle is going to connect these things together. And we're going to imagine that the circle is coming out of the board here and then going kind of back behind the board there. It should look more like an ellipse than a circle. And it should look better than I've drawn either way. But let's see if we can figure out what this whole cross-section business is saying. It says the cross-sections perpendicular to the x-axis. So here are cross-sections perpendicular to the x-axis. Those are all of our slices going right through the x-axis perpendicularly. And it says that they are squares. So what we're going to do is draw some squares that are coming out of the board, but they'll be kind of going up away from the xy plane that I've drawn here. So we want squares. So for example, if I had this particular cross section right here, I want a square where that's the base. So the shape now comes up out of the board, and then connect the dots, and we've got a square coming off of that circle. If I were to try to draw a square coming over here, would it be bigger or smaller? That's one side of the square. It's going to be a lot smaller. So we get all these kind of different sized squares. And it's hard to see in a 2D space, especially when I can't even draw a square, but we'll go ahead and take a good look at this thing through a Mathematica demonstration. You can download this thing for free and then play with it to your heart's content. Here is our picture right here. That is the shape that we get. If we look at it from above, technically we just see the circular base. But as we rotate it around, we can see all of these black lines here are these square cross sections. And so we have squares that are really small here. The squares get bigger, bigger, bigger until the middle. That middle square is right there, coming out of the board, but right there on the y-axis. And then again, they get smaller over on this side. So we get kind of these two very sharp lines on the corners of the squares. But the whole thing is curvy, which is weird because it was squares. So this is the thing we're trying to find the volume of. Okay, so we're trying to find the volume of this thing. Here's the basic idea. We're going to use this formula that we skipped over here in number 9, volume formula. I'm going to change the letters for just a second. Instead of the y's, I'm going to make them both x's. x's, all of these y's will change to x's. The formula is perfectly fine with y's up there, but it says if for each x inside of the interval CD, the cross-sectional area of a solid perpendicular to the x-axis is some formula. I know it looks crazy, but there's some formula for the area of each of our squares. We can take a look at our picture again. For the squares that are over here near the far right, the area of a single square is pretty small. And then the areas of these squares over here towards the middle get bigger, and then they get smaller again. But maybe there's some formula we can come up with in terms of x. If we are just sitting at a particular point x, like maybe when x is a half, the square has a certain area. But then maybe when x is 0.9, it's a much smaller area. Maybe we can come up with some formula that will tell me the area of the square as a function of what number x we happen to be sitting on. If by some miracle we can do that, and if we call that formula this highlighted thing up here, a of x, area at x, then it turns out the volume of the entire solid is given by this. And I want us to believe that formula is true. Think of what it might have come from in terms of the summation. So a of x just came from a of x with our artificial subscript down there. The dy, well, sorry, let's change that to an x as well. Change that to a dx. The dx, where did it come from? Yeah, the thickness. It came from a delta x. And so what we would have here is instead of having infinitely many squares, which is what this real shape is composed of, maybe we would have 10 squares. And so the squares, the shape wouldn't look nearly as smooth as this one does. It would look very blocky, almost pixelated. But the volume of each of those kind of blocks would just be the area of a single square times the thickness. It would just be a bunch of shoeboxes stacked on top of each other. And so if you knew what the area of a single square was, you could multiply by the thickness. That would approximate the volume of the part of this real shape. And that's all that this formula is doing. It's saying take the area of one square, multiply by a little thickness to give it some volume. Then take the area of the next square, multiply by the same little thickness. Add up all those volumes, and then it turns into an integral. So maybe pause the video or think about that some more after we finish this next example. It's an important idea to me. That we kind of buy into this idea that we should be finding the area of a generic square and then integrating it. So let's do that down here. So let's go ahead and call this point right here our generic x. I've drawn one purple square there, but you got to imagine it has a little bit of thickness, so it's got some volume. And the goal is to find the area of the cross-section. Cross-sections in this problem are all squares at x. So we're trying to find a formula for the area of the purple square, but not just a specific one, but a general one in terms of x. And then we're going to sweep x left and right. Okay, so let's see. The area of a square, we know the formula for that. That's one of our easy ones. That's going to be the side squared, whatever the length of one side is. And so the length of one side is from here to here. Now, would you call that an x distance or a y distance? That's a y distance. The thing that's staying the same on that blue line is x. X is always the same from here to here, but the thing that's changing is y. So I've got some y up here at the top, and I've got some y down here at the bottom. And if I can find those and then subtract them, I will find the length of that blue segment. So that's what we're going to do. We need to find y at the top, subtract y at the bottom, and then square it. But we know that x is our kind of driving variable here, and at the end of this game, we're just going to let x sweep right and left so that we get the whole volume of this shape. So I know it says find y at the top and y at the bottom, but these all need to eventually become in terms of x. X is the true variable we're going to end up getting out of this because x is our driver. Okay, so how do we find y at the top and y at the bottom? Well, that red thing right there was a circle that was given to us. And the equation was x squared plus y squared equals 4. That's part of the problem. So what letter are we going to solve for? we're going to solve for y. So y squared is 4 minus x squared, square root of that, and we just get square root of 4 minus x squared. But don't forget, when you take the square root of an equation, technically you're supposed to put in that plus or minus. That plus or minus is the top and the bottom, respectively. So we can now fill in our formula right here. So remember, we were squaring something, so it's just a big thing squared. Y at the top is equal to root 4 minus x squared minus negative root 4 minus x squared. So we did y at the top minus y at the bottom. And it's maybe no surprise, actually, those two combine and give us 2 of them. And you might have just used the symmetry to figure out that there was 2 of them. Okay, that's it. So that's the area of the square. Any particular x you pick, stick it in here, evaluate this expression, including the squared, you will find the area of that particular purple square. According to our formula up above, what we were supposed to do was stick on the dx. That dx was multiplying the area by the thickness of that square. That's how it goes from being a 2-dimensional area to a 3-dimensional volume. Okay, so then the rest of this is fairly mechanical. All we have to do is stick into our formula, that integral of a of x dx. So let's do that here. The volume of the crazy shape, the entire, we'll call it the funky shape, one that I had an awful hard time drawing. According to our formula, it's the integral of the area function dx from some number to some other number. We just got to plug in. Integral. The area function we just came up with is up there in blue, 2 root 4 minus x squared squared. That's the area of a single square. Dx at the end. And the last piece of this is finding the limits. So again, you imagine x driving, sliding left and right. How much is the smallest x at the far left? That's a -2 out there. And at the far right, +2. You could also use more symmetry and double the integral from 0 to 2. So -2 to 2. And it's kind of funky here that this is actually an integral, again, we can do by hand because that square cancels the square root. So if you want some more practice with antiderivatives, go ahead and do this one by hand, squaring everything in there first. Don't forget that the 2 here gets squared. And then you'll get some number. And then if you want, you could go back and use your calculator and just type in this integral and make sure it gives you the same number. All right, so there are 2 examples left in the notes for this packet. I have a meeting I need to go to in just a couple of minutes. So what I'm going to do is end this video here. And then the second video will start with the 2 problems we haven't yet done. And then it will be the class that we're supposed to do on Friday.